So I will recall some facts that we saw about nilpotent groups. First, let me remind you that we have the definition of distorted element or algebraically parabolic. If gamma is a function generated group, so there is the word metric, the shortest, the length in the Cayley graph, or the shortest expression. We generate those, and gamma is called algebraically parabolic if this is sublinear. Okay, and we saw two facts. So if gamma acts on X by isometries, and gamma is algebraically parabolic, then gamma is parabolic or elliptic. So in particular, if gamma is no fixed point, then it's parabolic. And second thing we saw that if gamma is nilpotent, of class K, so everybody understand, right, what it means? Then Ck minus 1 of gamma. So this is a general fact about nilpotent group. Consists of algebraically parabolic. Okay? And here we had some computation with commutators. So that if you have an element here, you can express it as product of commuting commutators and blah blah blah. And when you take powers with it, you can do it much more effectively. So some commutator identities which I personally don't like. But we have this fact, and the corollary is the following about group for isometries corollary. And let's suppose that we deal with manifold. So if gamma acts on X at a Hadamard space freely and discretely, and let's say gamma is nilpotent, so let's call it delta. Let's get and delta is nilpotent. Then either the center of delta contains a parabolic element, or delta consists of elliptic element, consists of a parabolic element. Delta is abelian and consists is abelian, commutative, and consists of hyperbolic. There are no parabolic. Okay? Of hyperbolic. Okay, is this obvious? Is this okay? Let's it follows from that. So now delta is nilpotent group. Okay, first, if it is not abelian, then look at Ck minus the last in the lower central, in the decreasing central series. Look at the last non-trivial group. It must consist of parabolic, algebraically parabolic, and therefore parabolic element. But it's inside the center. because the next state is trivial. So you have a central parabolic element. If it's parabolic and it has a parabolic element, then again you have a central parabolic element. If it's abelian. And if it's abelian and if you don't have parabolic element, then you are in the second case. So either you have a parabolic element in the center, or you consist of a parabolic element but you are abelian. So that's the only two alternatives. By the way, we will use this to prove the theorem, but to the proposition, but before that, the example that Shachar asked me why the minimal set is not flat, it was a correct example, but maybe not the best one. There are much simpler examples. Before we go on to this, so consider, in general, it's a good candidate for example, consider H2 cross H2. That's the symmetric space. And now you can have an isometry which acts by translation on a geodesic on the first factor by trivially fixing pointwise second factor. You see it has many x's. You have one axis here, but you can choose any point here. So any different point will give you a parallel axis, and what you have is R cross H2 and of x's. So this will be actually a stable isometry. But if you want something which is not stable, then don't act trivially on this H2, but rotate it. Now, if you rotate by irrational angle, then it's stable and you have only R. But if you rotate by rational angle, then you have R, but some power of it will have R times H2. So the minimal set will increase. So it's example of both things. So stability and the fact that the minimal set is not flat. So let's come back here. So another thing that I want to recall you, we discussed commuting isometries a lot, but let me just recall some obvious facts. So if alpha and beta commute, then the level set, then the d alpha is beta invariant. Okay, d alpha of beta x is the distance between beta x to alpha beta x, which is by commutativity the distance between beta x to beta alpha x. But beta is an isometry, so it's the distance from the x to alpha x. So d alpha is beta invariant. And therefore, the level set d alpha less than t, this is a convex set, is beta invariant. And the minimal set, when the displacement attains the minimum, is beta invariant. But also we saw that a corollary of that is that first, if d alpha less than t 1 is non-empty, and d beta less than t2 is non-empty, then it implies that the intersection d alpha less than t1 intersection d beta less than t2 is also non-empty. And so on for minimal set. If the minimal set of alpha, if alpha is hyperbolic and beta is hyperbolic, then the intersection of the minimal set is non-trivial. And the reason for that is we did it. So let me just recall. So d alpha less than t is convex and beta invariant. So the projection let's call it A. The projection to A commute with d beta. No, the projection of A commute with beta. if you have an element x and you look at the projection, this will be pi a of x, and then you have beta x, and you look at the projection pi a beta x, I claim it's the same as beta of pi a x. It's because this set is invariant and the projection is geometrically, but this commutativity implies that, because this and also pi a shrink is non-increasing. The projection to a convex set is non-increasing distances, and therefore if the beta displacement here is something, here it will be at most is something, it will be smaller in general, and therefore you have this properties. Okay, this.
So we've seen that the minimal sets intersect and the contain, and it's enough, right?
What?
We've seen that the minimal sets intersect.
Yeah, the minimal set intersect, but I want to say it more generally because maybe I want to discuss also the case where there are no minimal set. The parabolic element, you don't have minimal set.
You're not assuming the same symbol now, okay.
Yeah, I don't. Okay, now we want to prove this dilemma that I raised. So we have these two cases to consider. Okay. So we call dilemma. We have delta generated by gamma 1 and gamma n. It's virtually important. And x was a point in x, and we want to find the directions which increase distances or non-decrease distances, and increase them if you're not in the minimal set. Okay. So what is the proof? So first, suppose that so let n inside delta be normal finite index and be plotted. And you can say that the index of finite index at most m, you can say. Maybe I don't even need normal here. It doesn't matter. Now there are two cases. Either there is a parabolic element, or it consists of a parabolic element that it's a balance. If there is a parabolic element, then there is a parabolic element in the center. So case 1, n, the center of n contains alpha non-trivial parabolic.
You mean contains, right?
Yes.
Contains non-zero.
Contains a, yes. There is an element in the center which is non-trivial and parabolic. And let's assume that we have representatives. We have let's say delta 1 up to delta k are coset representative of n. So delta is the union of this joint union of delta I delta, where delta I goes from 1 to k.
Italian.
What?
Italian.
Delta I n. That's coset representative for that. And then I defined a function phi from x to r. I define it to be phi of x will be the sum I goes from 1 to k of
2n.
sorry? No, 2k of the displacement function of alpha conjugated by delta I. So this is, if you want, this is displacement of delta I alpha delta I inverse. Okay? Recall, alpha was central inside delta. So if I conjugate alpha by elements in delta, I don't do anything. But if I conjugate them by different coset representations, maybe I get something. But I claim phi is gamma invariant. Do you agree with that? Phi is gamma invariant. Okay.
Wait. Who is gamma?
Delta,
Gamma is delta.
delta. Phi is delta with no gamma. You agree with that, or I should write one? Maybe I should write one. So let's say let's actually call them this is the same as the sum I goes from 1 to k of d alpha I x, where alpha I is delta I alpha delta I inverse, and all these alpha I are in the center, because alpha was in the center, and so all these alpha I are in the center, and so therefore they commute with each other. And but if I conjugate, okay, let's look at phi of gamma x is phi of gamma x. I can write gamma as delta I0 times beta, where beta is inside n, right? So it's the same as
Probably wrote beta delta I0.
yes. And then so it's a phi of beta delta I0 x, and it's the sum of d
D of gamma x, d alpha of gamma x is d of conjugation of
Yeah.
alpha by gamma of x.
what do you say? D, yeah.
D alpha of gamma x.
D alpha of gamma x, yes.
This is d of gamma inverse alpha gamma of x.
This is d of alpha gamma inverse, right? Gamma inverse alpha gamma of x, right? Okay, and from this, prove this claim by yourself. Okay, you just when you replace by gamma, it's the same as conjugating by gamma, and then it's just permuting this function. So you get the same value. I will confuse myself. So I leave it as an exercise. So this is exercise. And but what you need is this. Do this exercise and then okay. Next, so it's a gamma invariant function, and now moreover, phi does not attain a minimum. So if we assume that alpha is parabolic, then suppose that rho of alpha, if you want it, the infimum of d alpha, is a, then look at d alpha less than t, where t is strictly bigger than a. So this is the convex set, and this intersect. You look at this intersection, I goes from 1 to k of d alpha I less than t. It's a finite intersection of convex set, and this intersection is non-empty by what we said before, because the alpha I commute. They commute. Each of them is parabolic with the same norm or the same rho. They conjugate to each other, and the thing commute, and so you see, so this is non-empty, but when you take t smaller and smaller, you take t arbitrarily close to a, this convex set will go to infinity somehow. So this if you want goes to infinity when t goes down to a. If you would draw the picture, so this is the Hadamard space, and you have this is where d alpha is less than t. And you have finitely many of them, you intersect them, and you get smaller and smaller set that converge to a point in infinity. Basically what I want to say is that phi does not assume the infimum. So phi does not assume its infimum, and if infimum of phi, actually infimum of phi will be k times a. That's another exercise, because the infimum of d alpha is a, and I take k times this, the infimum of phi will be, will it be exactly that? I think it will be.
You just moved it when you said it's not empty, the intersection.
Yes. Right, yeah. Okay. The infimum is k times a, and it's and if you look at phi less than t, where t is bigger than k times a, so this is convex, non-empty, and gamma invariant, or delta invariant, and this converges, so every point will be out of this when t goes down to ka. So you see, it will be, this convex set will go to infinity, and if I look at the distance function from this convex set, so define psi of x will be the limit when t goes down to k times a of the distance function of x from phi less than t, but you need to normalize it. So we don't want it to go to infinity, so you normalize by d x0, you fix some point Okay. So by saying we discussed this converge when t goes, this limit is a Boltzmann function. Psi is a Boltzmann function. It will be or a Hall function, like a distant function from point infinity. So we said that the properties of Boltzmann function, it's characterized by being convex, smooth, and the gradient is of norm 1 at any point. That's characterized Boltzmann function, and you see that this will hold here. So this will be a Boltzmann function. So we find a Boltzmann function which is a gamma invariant. It's because phi was gamma invariant and all this sublevel set was gamma invariant. So we find a Boltzmann function which is gamma invariant. And from this, we can deduce what we wanted. In the first case, which the second case is very similar, but let's see. So I claim that now we have a point x. I claim that the gradient of phi at x, how do you know it? At x is the vector we want. Actually, it's equal to, it's a Boltzmann function, so, not phi, psi. It's a Boltzmann function, so it's already as norm 1. The gradient of psi at the point x is what we want. Why? I claim that it's what we want to show. We want to show that the gradient of d gamma I with n is bigger than 0, and this is because this function was gamma invariant. So the level set of it was invariant. Any maybe I need help here. Do you see it or not?
What is gamma I again?
Gamma was the generator. So gamma will generate already gamma 1 up to gamma k, gamma n.
Delta, yes.
What?
Wasn't it delta?
Sorry?
Delta was generated.
Delta. Now I claim that it doesn't matter, but for any gamma in delta, I claim that the gradient here will be non-negative. For any gamma in delta. And why is that? Because what is this function? This function is a distance function from a convex set that shrinks to infinity. Suppose I'm here, and you know what? Maybe it's true, but maybe it's better not to take t to the limit, but let's leave this convex set. Okay, we have x. We already have x. We have a point x, and we can look at this is phi less than t. I don't take x to the limit, and now I look at the projection here, and I claim and n hat will be the inverse direction from the projection, and then I claim this n hat will work as well. Why? Because this set is gamma invariant. So it's by things that we already saw. So gamma takes phi less than t to itself. It's a convex set. So it's and then you see that that d gamma is increasing or not decreasing on this, d gamma, if this is a geodesic C, C of not T but another parameter, C of S, then d gamma consists of C of S is increasing or non-decreasing. It's non-decreasing because the projection here shrink distances. So I look at the distance between these two geodesics, it increases. So d gamma is increasing, and therefore the gradient d gamma times c dot, which is what we call n hot, is so this is the direction. I could do it actually with a point at infinity, and then we can do it either way. But then we find a direction such that it's good, it has this inequality, but I claim that it's more than that. It's non-negative, but for one of them it must be strictly positive. Then I claim this is true for any gamma, and for at least one I from 1 to n, we have the gradient of d gamma I times n hat is strictly positive. And why?
So you only need t small enough so x won't be.
So x will not be, yeah.
That's the only thing you care about.
It's only
And
yeah. And then I claim that the gradient of at least one of the generator times n hat, if you want the directional derivative, is strictly positive for one of the generators. Why? So here I use some analyticity of the metric. Suppose that it's 0 for each of the generators. If the gradient is 0 for each, if the directional derivative is 0 for each of the generator, then it will be 0 for each element in the group. In particular to this alpha. But it's not 0 for alpha because we know that the displacement of alpha here is smaller than here. So the displacement alpha and the displacement, it's a convex function. If it increases, then the derivative is also monotonically increasing. So if it's 0 here, it will be 0 all the way, and it's a contradiction. So I
Well,
prove.
do we use analyticity here?
I don't need analyticity here. Maybe not.
You used convexity?
No, I don't. Yeah, you're right. I think maybe here I don't need analysis. Yeah, here I don't need it. But I didn't prove the lemma, but I proved that for all generator it's non-negative, and for one generator it's positive. Okay. This is what we do if we have a parabolic element. Now let me say that we can do exactly the same. I'm hand waving. We can do exactly the same if we don't have parabolic. If we don't have parabolic, then all this group delta, all this group n, consists of hyperbolic element, and it's a commutative group. And then, if there are no parabolic, I take. Let me continue. If n has no parabolic, then it's abelian. Take again alpha inside n, non-trivial, and look at alpha I be alpha conjugated by delta I inverse, like before. And now, instead of looking at Guzman function, we look at the minimal set. The intersection of minimal of alpha I will be some subset which is non-empty. And by the assumption, x will not be in the subset, so this I need to see if it's coherent to my assumption. My assumption was that X was not in the minimal set of any stable, blah, blah, blah. This I need to check, but if we formulate it properly, then X will not be in this minimal set. And you do exactly the same, but instead of taking the projection to the convex set, to this convex set, you take the projection to this convex set, which is in the intersection of minimum of the displacement function. Okay, this was a bit fast, and we achieved less than we wanted. What did we achieve? We have this generator gamma 1 up to gamma n, and we find a direction which the displacement of each of them is non-negative and of one of them is positive. Okay, but then look at, suppose the displacement of gamma 1 is positive.
This n is the direction at the point x.
Yeah,
Depending on x.
it's at the point x. Yeah, it's at the point x. And now, look at the group generate. Suppose this n is, the gradient of gamma 1 is strictly positive, so look at the group generated by the rest. For them, you find a different direction which is good for gamma 2. Maybe it's there. So this is n1 and this will be n2. And then you find n3 which is good for the S. And then but this n2 maybe is not good for gamma 1. But I don't care, I take it much smaller than n1. Take n2 whose norm is not hat anymore, it's not normalized. So take n2 whose norm is much smaller than n1. So it will not interrupt. So n1 already increased gamma 1 and the rest will not destroy that. n1 does not decrease the others. And n2 will increase gamma 2. And then n3 will be much smaller than n2, so it will not destroy the fact that that gamma 1 and gamma 2 increase, and it will take off the rest. So the final n will be the sum of n I, and that's how we find the direction. Okay, this
normalized.
Yeah, this you can normalize. Yeah, this you can normalize. Okay, this was a bit fast, I think, but when we write the notes, we'll try to do it more detailed. At least I think the idea was obvious. Okay, we have 10 minutes. I want to tell you now a magical way that I learned in Barnard-Schroeder book, how to use this direction to define a deformation return. A priori you think, okay, we have the direction, that's where we're going to flow, but the direction was, maybe it's not even continuous when you change x. Okay, for one x I can take the best direction. But then if I change x, somehow I change the group. Because Margulis lemma tell me that the elements which small displacement at x, smaller than 2 epsilon, is virtually potent. But maybe when I change x, suddenly there is another element. And suddenly one of the elements, the group change. So suddenly the best direction may jump. And it really jumps. I mean, if you think of a manifold, you want to increase the injectivity radius because you think the injectivity radius is because of one loop, but when it's large enough, maybe now it's another loop becomes the smallest one, and so you have jumps in the direction. Actually, the injectivity radius is a continuous function, but it's not smooth function. It's not C1. So how do you use this direction to find to produce a deformation tract? And this is a beautiful and simple idea that from Barnard-Schroeder book. And it's like that. So define the following function. So let f of t from r plus to r from the positive to the non-negative. Be smooth function. Non-increasing. Let's say f prime is strictly smaller than 0 on 0 epsilon, and f is constantly 0 on epsilon infinity. So here is the graph of the function. So this is epsilon, Mogul is constant, and the function is like that. But it's smooth here. It's smooth everywhere. It's infinity. It's not non-analytic, but it's infinite. But this is f. And now define psi. Let psi from x to r be the following function. Psi of x will be the sum of all gamma in gamma minus the trivial element of f of d gamma at x. So it's an infinite sum, but I claim first that psi is well defined. Okay, properties. So first, psi is well defined.
Epsilon here is the same epsilon from before?
Yes. Epsilon is a Margulis constant. So this is the Margulis constant. You can take half, twice, whatever. So psi is well defined because this is an infinite sum, but for any point x, there are only finitely many gammas such that the displacement is less than epsilon. Because the action is by this discrete group, and it acts properly discontinuously, for any x there are only finitely many with displacement less than epsilon, and those with displacement more than epsilon contribute 0. So it's a locally finite sum. This is a locally finite sum. Okay. Secondly, psi is small. Third, okay, this is really nice. What is the set psi equals 0? Can you tell me what is this set? It's exactly the thick part. It's exactly m greater than epsilon. It's exactly the epsilon thick part. If I'm in the thin part, it means that the displacement of one element is less than epsilon, and therefore the function is positive. So this is exactly the thick part. And the last thing is for x inside x minus n tilde, and n tilde we need to think precisely what it is, but n tilde is a stable manifold, should be a stable manifold. The gradient of psi at x is not 0. Because there is a direction as before. There is a direction such that the directional derivative of each of the generators of the y, any point x, I for any point x, I look at all the elements whose displacement which contribute positive value to this function. So they generate a virtual important group by the Margulis lemma, because all of them has displacement less than epsilon at each. By the Margulis lemma, it's a virtually important group, and therefore by the proposition that we did before, there is a direction which is good. It's coherent with the displacement function of each of them. So in this, the directional derivative of the displacement of each of them is positive. What is the direction? This follows from the previous lemma, because the gradient of psi times this n from before equals sum of f prime at d gamma I of at x. Well, I suppose that gamma 1 up to gamma n are exactly the elements d gamma I less than epsilon. That's gamma 1 up gamma 1 up to gamma n is a finite set, which it's all the gamma in gamma minus identity such that d gamma is less than epsilon.
Okay.
D gamma of x. So I look at this set, it's a finite set, it generates a virtually important group, and then this is exactly a gradient of d gamma I x times n for n hash. And this was positive for each of them by the previous lemma. There is some n hat, and this was negative, so it's a sum of negative number, so it's not zero. Okay.
It's not n.
What?
Just it's not gamma 1 to gamma n. No, I mean,
Gamma
oh,
1.
you use the okay.
Yeah,
Gamma 1 to gamma
no, no.
k, that's the...
Gamma
Gamma
1
something, never mind.
to gamma n, which depend on x. Something. Yeah, it's all. Yeah. Right. It's a. Okay. Okay. It's a finite set. Yeah. It's n is actually. Okay. It's
It was called k before.
it was called k before, and it's depend on x.
It's called manifolds.
Okay. And anyhow, this. Okay. So what's the word now? And I will not write it because I'm cheating a bit. The word now is to use Morse lemma. So Morse lemma is a fundamental lemma for Morse theory. Tells you that if you have such a function, which is if you have a Morse function, if you have a function from a subset of a manifold, or you have a function from a subset of a manifold to R, and you have two level sets of the function, and the sub-level sets are both compact, and the gradient, and they're both manifold with boundary, and the gradient of the function is non-zero on this interval between them, and also on the boundary you need, then there is a deformation retract from one level set to the other. And the idea is to flow along the gradient of this smooth function. But the problem is that we cannot use Morse lemma because the gradient is non-zero. This is not true. It's true for x, which is not here, but also not in the thick part. So, okay, we will come back to this next time, but there is a deformation retract to any positive sublevel set, but I don't know it yet for the zero sublevel set. But the way to finish is something that Shachar told me a couple of weeks ago, that I can, and I will do it next time, but the idea was first to use this function to do the deformation track to a small neighborhood of the thick part, and then to use the fact that we understand the thick part and we can construct what is called a Kolar neighborhood, which I'll explain next time, and continue from there with another deformation. So you first do this until you are very close to the thick part, which you can by Morse lemma, which I will state Morse lemma next time and use it. Now I'm just hand waving. But this is not enough for the deformation right to the thick part, but it's almost enough. And then you can continue with another idea. And so this is what we'll do next time. We'll finish this deformation right to the thick part. But then I will need to think, because I don't know exactly how to control the boundary of the thick part. I know to control the boundary of other sets, which are similar to the thick part. So we need to deal with that. We need to deal with it. So this will be good enough if we want to do like Baumann-Gromov-Schroeder to control the Betti numbers. But we want not just the Betti number, we want to control the torsion, we want to control the homotopy type, we want to control more things, so we need a good understanding of the boundary of the thick part. And we don't have it, but we have a modified version of 16 compositions, which we have better understanding of the boundary. But then there is some modification we need to do. I think everything is possible, but I need to think about the details. But the idea is, the main ideas were given today. So more the details that we need to change there. Okay, that's it for today.